manage to put 3% in weight salt in here, then this 2 mega ohm will go down to 2 ohms, 1,000,000 times less. So now, the light bulb will be happy like a clam at high tide, because 2 ohms here, plus the 800, the 2 is insignificant. And this is what I want to demonstrate to you now, the enormous importance of increasing ions. I increased ions here by heating the air. Now I'm going to increase the ions by adding salt. And so the first thing that I will do is I will stick this in here. There's the light bulb. And I make a daring prediction that you will see nothing. There we go. Nothing. Isn't that amazing? You didn't expect that, right? Physics works. You see nothing. If I take the plates out and touch them with each other, what will happen? There you go. But this water has such a huge resistance that the current is too low. Well, let's add some, not pepper, add some salt. Yeah, there's salt in there. It's about as much as I would put on my eggs in the morning. Stir a little. Ah, hey, look at that. Isn't that amazing? And when I bring them closer together, they become even brighter. Because L is now smaller, the distance is smaller. Bring them farther apart. It's amazing. Just a teeny weeny little bit of salt, about as much as I use on my egg. Let alone, what the hell, let's put everything in there. Let alone when I put everything, then of course you go almost down to the 2 ohms, and the light bulb will be just burning normally. But even with that little bit of salt, you saw the huge difference. My body is a fairly good conductor. Yours too. We all came out of the sea. So we are almost all water. And therefore, when we do experiments with little charge, like the Van de Graaff, beating a student, then we have to insulate ourselves very carefully, putting glass plates under us or plastic stools to prevent that the charge runs down to the earth. In fact, the resistance, my resistance between my body and the earth is largely dictated by the soles of my shoe. Not by my body, not by my skin. But if you look at my soles, then you get something like this. And it has a certain thickness. And this, maybe 1 centimeter. This now is L in my calculation for the resistance, because current may flow in this direction. So that's L. Well, how large is my foot? Let's say it's 1 foot long, no pun implied. And let's say it's about 10 centimeters wide. So you can calculate what the surface area A is. You know what L is. And if you know now what the resistivity is for my sole, I can make a rough guess. I looked up the material, and I found that the resistivity is about 10 to the 10th. So I can now calculate what the resistance is in this direction. And I found that that resistance then, putting in the numbers, is about 10 billion ohm. So you will say, wow. Oh, it's 4 actually. Well, big deal. 4 billion ohm. So you will say, that's an enormous resistance. Well, first of all, I'm walking on 2 feet, not on 1. So if I would be standing 1 the whole lecture, it would probably be 4 billion. But if I have 2 feet on the ground, it's really 2 billion. You will say, well, that's still extremely large. Well, it may look large, but it really isn't, because all the experiments that we're doing here in 26100, you're dealing with very small amounts of charge. Even if you take the Van de Graaff, say, has 200,000 volts. And let's assume that my resistance is 2 times 10 to the 9 ohms, 2 feet on the ground. So when I touch the Van de Graaff, the current that would flow, according to Ohm's law, would be 100 microamperes. That means in 1 second, I can take 100 microcoulomb of the Van de Graaff, but the Van de Graaff has only 10 microcoulomb on it. So the resistance of 4 billion or 2 billion ohms is way too low for these experiments that we have been doing in 26100, and that's why we use these plastic stools and we use these glass plates in order to make sure that the current is not draining off the charge that we need for the experiments. I want to demonstrate that to you, that indeed, even with my shoes on, that means even with my 2 billion ohm resistance to the ground, that it will be very difficult for me, for instance, to keep charge on an electroscope. I'm going to put charge on this electroscope by scuffing my feet. But since I have my shoes on, I'm not standing on a glass plate, the charge will flow through me. You can apply Ohm's law. And you will see that as I do this, I'm scuffing my feet now, that I can only keep that electroscope charged as long as I keep scuffing. But the moment that I stop scuffing, it's gone. Start scuffing again, that's fine. But the moment that I stop scuffing, it goes off again. Even though this resistance is something like 2 billion ohms. Let alone if I take my shoes off. I apologize for that. If now I scuff, you can't even get any charge on the electroscope. Because now the resistance is so ridiculously low, I don't even have the 2 billion ohms. I can't even put any charge on the electroscope. It's always very difficult for us to do these experiments unless we insulate ourselves very well. And if somehow the weather is a little damp, we get very thin films of water onto our tools, and then the current can flow off just through these very thin layers of water. That's why we always like to do these experiments in winter, so that the conductivity of the air is very low, no water anywhere.
Here you see a slide of a robbery.
I have scuffed my feet across the rug, and I am armed with a static charge. Hand over all your money, or I'll touch your nose.
This person either never took 802, or he is wearing very, very special shoes.
See you on Wednesday.